Dear colleagues, today doctoral candidate Mikhail Blagov will defend the dissertation titled Exact Lock and Range for Classical Phase-Locked Loops. The opponent, Professor Leonid Chechurin from Lappeenranta Lahti Technical University. As a Custos appointment by the faculty, I declare the public examination open. Please.
Distinguished Custos, honorable opponent, ladies and gentlemen, please let me present my findings on the topic of exact lock-in range for classical phase-lock loops. My supervisors are Nikolay Kuznetsov, Pekka Neittaanmäki, Timo Tiihonen, and Renat Yuldashev. So the synchronization as a phenomenon was first noticed pretty long time ago. First mention of it is Horologium Oscillatorium, 1674 by Christian Huygens, where he put two clocks on the same beam in a ship. And he noticed that after some time, these clocks are getting synchronized state. So nowadays, we are mostly using master-slave synchronization, which was first used by Sir Edward Appleton, who studied ionosphere and actually proved that it exists, got for this Nobel Prize. And this is somehow the system that allows to synchronize one oscillator to another. So currently we have wide usages of these systems in computer architectures, GPS, and others. And first mentions in engineering literature belong to Viterbi, Gardner, and later Shagildan Lihovkin in the start of the second half of the 20th century. So let me put one example on it. Multiprocessor system is controlled by a set of phase-lock loops which allow processors to work in synchronous mode, but it was not so good when it just started. So for example, like 20 or 25 years ago, every one of you could have a computer with a turbo button, and this turbo mode was not guaranteed to be stable. There was a special line in the instruction to this button. So you cannot just press it and everything will be okay. Sometimes it can be not stable, and that's because of the PLL operating not in a good mode. So we will consider mathematical model of phase-lock loop in phase space. It's a system of differential equations which has some parameters, constants, and so on. The main thing here is the frequency error, which is noted as omega E3. This is the difference between frequencies of reference oscillator and the controlled oscillator, and we will define our operating ranges for this thing. So the mainly studied problem in my dissertation is Gardner problem on the lock-in range. It was stated in 1979. So if for some reason we can do a fast synchronization without sleeping cycles, this is a good, and this is called for as a lock-in frequency. Rigorous mathematical definition of this was given by Nikolay Vladimirovich and co-authors in 2015, and now we study the lock-in range in accordance to rigorous mathematical definition. So research questions for my dissertation are related to three variations of phase-lock loops, two of them with proportionally integrating filter, active actually, and one with the lead lag filter. So for two of them with piecewise linear phase detector characteristic, I calculate exact lock-in range value. And for another one with the phase detector tangents, I prove that the lock-in range of this system is infinite. So the structure of my work as follows. Three main research questions are covered by 5 publications. exact locking range for proportionally integrating filter is covered in Article 1. Articles 2, 4, and 5 are related to lead lag filter, and Article number 3 to the system with the tangential phase detector characteristic. So the main definitions that we'll study are ranges, actually hold-in range, pull-in range, and the lock-in range. Hold-in range corresponds to the tracking mode of the system when you are in stable equilibrium, and the system, after slightly changing the frequency deviation, can follow it. Pull-in range corresponds to synchronization from any initial point, and the lock-in range, the most interesting, it's fast synchronization in one beat without cycle slipping and other terms, but we will use this equation as this inequality to define the cycle slipping. So the trajectory of the system must stay in the stripe of 2p wide. It's important to mention that intervals are included into each other, so lock-in range is included into pull-in and subsequently into hold-in, because studying fast synchronization without synchronization, of course, is impossible. Well, there are some estimates already done for the lock-in range, linear estimate by Gardner and Best, and the years of these publications are quite new, and the book itself is very popular in engineering. And also Alexandrov estimate, non-linear estimate, which was done in 2016. So he used a slightly different definition that simplified calculations. So what's the lock-in range algorithm to calculate? Let's say we don't have any analytical procedure and have a numerics only. So we are in synchronized state, phase lock loop is in synchronized state, and then you abruptly change the frequency to the opposite side. Then just watch at the system behavior. If it's synchronized without the cycle slipping, then it's okay, we are inside the lock-in range. Once the frequency difference got too big, cycle slips appear, and we are outside of the lock-in range. So this is the problem, and the boundary is somewhere in between those two last switches. What does it mean in terms of phase portrait? Well, we have several pictures here. One of them on the top left is synchronization without cycle slipping. We are in the black trajectories, and in synchronized state can be either unstable or stable. And after the switch, the phase plane shifts, and the equilibria are now new, and one has to track the synchronization process to obtain whether it slips cycles. So the desired situation that we are in the boundary of this, and it is described by separatrix behavior. So if one of the synchronization trajectories comes to an equilibria, saddle equilibria actually, this is the boundary of the lock-in range. And it's easy to be calculated now. So let's get to the results. First, regarding PI filter and piecewise linear phase detector characteristic. Model for the filter, here is the transfer function and also the differential equation, piecewise linear phase detector characteristic, and the result, theorem that exact lock-in range can be calculated by some quite big formulas where one of the letters should be defined by solving an equation. Okay, how did I obtain this result, you would ask. First of all, we have to somehow transform the system, do some nonlinear variable change, and then divide equations one by another, which allow this system to be integrated as actually phase detector characteristic is linear and system is piecewise linear. So we can integrate it on linear pieces and then describe the separatrix behavior. We're actually interested in ordinate at this point. Okay, no problem. We have antiderivatives and we can solve subsequent Cauchy problems to obtain necessary value. So this is how it's done, and this theorem allows to build an engineering diagrams that help to define the local range based on the system parameters. So the red here on this picture is an estimate by Konstantin Alexandrov. Green is estimate done in this work, and blue is linear estimate by Roland Best. So as you can see, linear estimate allows cycle slipping for some parameters, and it was significantly enhanced in my work. So complete diagrams can be built for usage, and that's it for this system. Let's go to another one with the tangential phase detector characteristic and the same filter. Model slightly changes, we change characteristic, and as you can see, such system was patented in 1965 by North American aviation engineer. So theorem here is rather simple. The pooling and the lock-in ranges are infinite for this system. To prove this, I used the Lyapunov function. This is for pooling range global stability, and analyzed phase portrait and on the border, and proved that all the trajectories in the phase space tend to equilibria in the same period as they are originated from. So that's rather easy, and as we go into lead lag system, the model is quite more complicated here, but the approach is actually the same. We need to shift phase portraits and estimate separatrix, and after some denotions we get to a rather complicated theorem that allows one to calculate the lock-in frequency by solving two equations, actually. They are not differential, so it simplifies. Newton methods work fine, and it's okay to solve it numerically with arbitrary accuracy. So here is the diagram again. Now we compare it to the pooling range. It's a known result. And to the linear estimate by Roland Best. Scale is logarithmic, so it's kind of looks non-linear on the diagram, but it's linear, yeah. And again, you can see that it was improved. So complete diagrams are built for the system, and the lock-in range can be determined on these diagrams. In summary, I would like to say that all the research questions I was working on were answered. I enhanced a couple of estimates of the lock-in range, and there was a system found which for the lock-in range is infinite. So as for future, there are still some open questions regarding the topic. First of all is analysis of the system with sawtooth characteristics. It's quite harder to be analyzed analytically and is omitted in my work, and also to consider application of the method to higher order filters. So it looks promising, and I think Mikhail Blagov will continue this work together with me later on. So thank you for your attention. Honored opponent, could you please share the comments my dissertation gave the ground for?
Thank you so much. Yes, Kostas, dear candidates, ladies and gentlemen. Thank you for calling me, and I have to give just maybe like a little bit bigger picture, trying to make an overview where the position of your work and maybe in the field of nonlinear control theory, and I'm planning also, will try in a few words to try to bridge what you are doing to what I have done a little bit, and then if possible we'll go together through the dissertation, because there are some questions and some maybe discussion points and even some mistakes found. Okay, would it be fine?
Yes,
so
please.
like I try to popularize as much as possible because possibly the whole world is watching us now, and so I try to position it in such a way that from time to time I come across to a collection of, let's say, physical phenomena. And they try to collect everything in one book, like you have this, for example, Maxwell, law, or they have, Coulomb law or whatever. But I always have a kind of problems to digest it, because definitely any nonlinear system is a huge collection of phenomena. And the more you study nonlinear system, new phenomena is revealed. So this reference book is a poor attempt to collect any possible phenomena in the world, because in nonlinear study of nonlinear system and what happening inside nonlinear system is definitely would need to reprint it many times. It is definitely I try to be dramatic or / romantic to say that nonlinear is like an unknown land. You enter all the time alone, sometimes without much support, and you have to understand. You have to find something. That's pretty exciting journey. At the same time, it's a huge golden mine of new conclusions that you can apply in real life and for new technologies. So it's definitely very important to study. It's full of new phenomena, and basically maybe so many inventions or so many applications and so many devices that changed our life are based on of new finding in nonlinear world. And actually I was trying to think what was the first, maybe the last big result in linear theory, and I find maybe Haritonov theorem. When they study stability of linear system on intervals, maybe, because after that, I didn't see a big theorem if it is linear theory. Mostly that is in nonlinear. One of also very exciting, breathtaking phenomena in nonlinear world dynamic system is called synchronization. I will also try to dramatize it a little bit. One of application of it that is actually literally question of life and death is a pacemaker. When you have to synchronize the heartbeat of your oscillator with the external. How do you define it? External synchronization, right? Yeah, like it's master-slave. Yeah, master-slave synchronization. I used to call it, but excuse my English, as I said. Yeah, I used to call it external synchronization, when you have to be synchronized with external signals. So, and that is just to in addition to a huge amount of applications that you listed as promising fields or fields where it is demanded. This is definitely one of them. And when you study nonlinear systems, there are, again, it's also always a kind of act of inventing. You have to invent a method to go through. It is never, in contrast with linear system analysis, you cannot guarantee it will apply results. Sometimes you have to invent the method. So, and on the top of everything, each time when you provide an exact, rigorous, theorem or exact boundary conditions or exact conditions of this phenomenon to appear, it's a big achievement, really big achievement. And I will try to sound a little bit entertaining. If you know what Neil Armstrong said when he landed on moon, he said, yeah, this is a small step for me, but a huge leap for humankind. I say each result in nonlinear theory, when it is exact result, would be definitely maybe not such a big step for science, but really huge leap for candidate who wants to prove their professionalism in this area. So that is definitely you have to be brave to enter this, and especially when you have a rigorous result. Because what I did was not rigorous. And here I'm bridging it a little bit to which results somehow made me come in here, and somehow could explain why I'm acting as an opponent. I studied nonlinear oscillations a lot, and what I did was the most evaluation. It was frequency domain. So I tried to evaluate the conditions under which certain phenomena could happen, and there was a list of phenomena, and one of the phenomena I studied synchronization also, and the result that could be most near to what you have been done was like we have oscillating system and we have external signal coming to it, and I could roughly evaluate the conditions of synchronizing, phase synchronizing in the range of frequencies of master signal and in the range of magnitudes of master signal. Roughly, there are no guarantees. These real results, of course, seems to be much more, let me call it professional, because mine was like engineering. There were no theorems in my dissertation, but that is possibly what we can try to talk. For example, you have this range in frequencies, but you are not talking about the magnitudes of signal. and maybe it is interesting to talk about. And also, my evaluations are rough, and it is like I even call it, if it's sufficient or necessary. I mean, it's a rough in first approximation, the range of frequencies in which synchronizing could happen like this. One difference, and we might talk about it, is we also considered like high frequency, low frequency synchronizing. It looks like what you are considering is also one-to-one synchronizing. So the frequency of because the area of application of synchronizing could be extremely larger if you consider not only one-to-one synchronizing. And maybe, who knows, maybe it would be the next step, whatever. Yes, hopefully I try to make a drama as much as possible and to say that, yes, it's extremely interesting, extremely intensive professionally, mathematically area of science with the applications, with the potential of applications, and even I was able to a little bit to follow the discussion. I will try to now to do this kind of fencing for the purpose of better science and the pleasure of the audience.
So thank you for such introduction.
Yes. If I can sit and we can go.
Yes.
If we don't mind, I suggest we go page by page a little, because initially I thought it could be we first go with small comments, like to warm up, and then we go to deeper discussion. I think we can go linearly, even in this non-linear dissertation, so page by page. Okay, then we go, but anyway, naturally we start with very simple things, because like typically we do some introduction, acknowledgement. It's very kind of interesting moment when you open a dissertation. The first phrase has a typo. I mean, the first very phrase of abstract, like phrase length are widely used. So are is used 2 times. I mean, this is again to prove that I read your dissertation carefully. And again, I have to say it's easy to read your dissertation. English, as far as I consider to be an expert in English, very smooth, understandable, almost no typers. I found actually 3. We'll go through them. But yeah, when I turned the page, when I saw that you have 4 supervisors, then I understood why you have typos, because typically if you have so many supervisors, nobody cares to read it because maybe another supervisor will read, right? So, and it is also another impressive thing. Yeah, 4 supervisors, I mean, absolutely legitimate. It's great. You are very lucky person to have so many advisors. Yeah, but it was kind of outstanding, I would say. Okay, then we go to maybe to list of list of articles. Again, as an expert, I need to say that all publications are nice. They are mostly collected in recognized journals that is supported by the fact that they all are U4-1 level, so it is a qualification level, and that is good. I went through them because it was sometimes it was impossible to understand what you want to say unless you have to read the publication. So very professional, no doubt. It corresponds to the level of the scientists and the way you done. Anyway, I need to ask some maybe hard questions. Yeah. So there are 5 publications, and there is no publication when you are solo author. If it had a publication when you have solo author, the question, did you do the job yourself, is not necessary to ask because you have solo publication. If you don't have solo publications, then I need maybe to ask why. Is it like a culture of doing things in mathematics, or why?
Well, it's not a culture, it's a culture of doctoral preparation, because usually you don't have a task set for you by your own. So, and the main mission of co-authors was to set the initial task, and then I solved it, and after that to verify and maintain scientific quality. My co-authors were helping me to get this ready.
Okay. There is, I mean, again, a culture of doing things, I would say, in physics, especially in experimental physics, the list of co-authors could easily exceed 1,000, literally, yeah. While, let's say, in engineering papers, yeah, it is okay to have a solo publication. And in general, do you have any solo publication in your record?
I have a patent.
A patent?
Yes.
Wow.
It's not a patent, but it's called program. Свидетельство on program.
Okay,
So,
in general, also, we cannot see how many publications you have in total, because I think it could be a good idea that you say you have 5 publications that are somehow related to the topic, but in total you have so many. How many?
8 or 9, something like this. Yeah.
Okay. And also, yeah, innocent question. So you have 4 supervisors.
Yes.
And 2 of them didn't make it to your co-authors of papers.
Yes.
I asked what was the reason. Yeah, like, yes, they were supervising, so you have to be somehow enriched. Yeah, but they didn't make it to the publications.
Yeah, sure. We are in Jyväskylä now, and it's quite hard to get all the stuff organized without the supervision in place. So I would like to thank once again Professor Tiihonen and Professor Neittaanmäki for the guidance here in Jyväskylä and for making this possible, as well as for making this particular text ready for publication and of, I hope, a high quality.
Absolutely understandable, and yeah, I would do the same. Absolutely, that's right. You write in your acknowledgement that thanks to all your supervisors for discussion. So definitely, that was a part of finding the truth. Definitely. So that is no doubt. Again, it's a bit, I would say, also the culture of this doing things different from university to university. But I mean, something that keeps my attention. I mean, is a reason to ask. That is like this. Okay, then yeah, maybe we can go to introduction. Yeah, and yeah, one bit interesting when you talk about applications and you list possible applications, that would be grids, that could be communication system, gyroscopic system, and you repeat it many times. Like, but by the way, it is used in yeah, and it's repeated maybe 3 times through the, but all the time references are different. So sometimes they are, I mean, the same.
Well, it has an intention actually. So first part of the introduction is related to the history of the topic, and this history contains not only the newest literature but its appearance in historical order. Further, I concentrate on more actual applications that are, better now. And of course, I don't talk already for the television, analog television, you mean, because this system was widely used there.
Signal,
yes. Yes, to just synchronize with the your TV set with what they have on the camera, yeah. But it's important to mention all those applications to understand the development of the topic. And this is what the intention of the first part is. And later on, I concentrate more on practical examples where we actually some of the tasks were set not only by my scientific supervisors, but also by engineers who apply these systems and who want to understand why it's working or not working.
Mm-hmm. Okay, understood. Thank you. Also, I was as an engineer, and I need to also maybe to have a kind of disclaimer in a way that although we both speak with a strong Russian accent, but my cup of tea mostly was engineering. So I try to be interested more in the applicational stuff. While sometimes I just simply hopeless to fly at your level of mathematical proficiency. But it is good. Maybe some everybody has his or her strong point. And I was interested in exactly what kind of applications there are. And I understand how synchronization is used. Hopefully, understand in electric grids, in signal transmission, also in gyroscopic systems. What is the business of synchronization? Why it is important for gyroscopic system?
Well, it's a kind of complicated question, but you have to synchronize 2 gyroscopes usually to get the system operating.
Clear. Now it's clear because I know pretty well what is gyroscope as a submariner. Former submariner, so there are 5 gyroscopes in a submarine, and mechanical gyroscopes, and they have to be definitely synchronized. That possibly was the case, but it is not master-slave synchronization, or it was a master signal to all of them. Do you know technique? I'm sorry, maybe it is not for mathematician. It's a hard question.
Yeah. For mathematician, you're right. It's a hard question, but I think there should be some kind of master gyroscope and others are just slaves,
Okay.
because it's reasonable if you know the parameters of the master to assume that parameters of the slaves are the same.
Okay, understood. And why yes, what is also difference with the technical dissertation, I would say, because say it is applied in gyroscopes, and then you describe how it is applied in electrical grids, and you explain in which electrical grids, but you just in electrical grids reference and gyroscope reference. So I wanted to understand what it is, but you just referred not, to a paper that is, again, in a way which is very professional.
Well, you know, if I put every application here in the dissertation, the introduction would be like 50 or 100 pages, and it would take eternity for you to read it.
It is very strong point of your dissertation that if you want to make it minimalistic as possible, then it is the case. It is really like this Pareto optimum, like you say. Like if you need to present 20% of text that would.
Well, you had all the formulas to read further, so.
Okay, still one also kind of funny question, but again, please understand that I try to read your dissertation very rigid as a scientific text, because we need to evaluate your, let's say, research, way of doing things. And what still it is very qualification text, but maybe you cannot help falling in a little bit, how to say it, popularization mode. And you sometimes you write in Italian scientist, and then later you say American engineer, and you add even like IEEE member, or even you give a name of the company when this American engineer worked. To which extent you believe it is important to indicate in such a rigorous text that this guy was from Italy, this guy from America? Do you think it's important? Does it add anything to scientific discussion?
I think it adds something to the value of the dissertation, because the topic is widely spread. And those notions like Italian, American, big company, just lets the reader know that it's used. It's used, it was used, and it's used widely. That's why I'm doing this. So I'm not trying to do some pure mathematics in vacuum. I'm trying to find an application of this. And this just lets this know. So if I would like to, just be in vacuum, I would start not from the introduction. I would start from the system of differential equations and just went with, 20 pages of formulas, and that's it, I'm done. The result is obtained, but, would it be interesting for you to read?
If it is a dissertation, yes. If it is a public presentation when you want to demonstrate, because you cannot, to my opinion, you cannot prove that it's widely used just telling that American engineer used it. In a way, if you ask proof, you need to calculate statistics of using, give some reference. But it's my humble opinion, whatever. So. Well,
this is the topic of statistical dissertation.
Okay, great. Anyway, but this again, if we do fencing, I would say that maybe in scientific test, especially qualification test, we have to get rid of, let's say, I think, we think, everything has to become. At the same time, because you also cite a Chinese researcher, and why you are not writing Chinese researchers? So that's like, but you prefer Italian for a reason or American reason or whatever. So that's either you maybe you demonstrate by each researcher, but otherwise it's a little bit captures my attention and becomes a reason to ask. But I'm happy to learn that IEEE member did something. Then next page, this is abbreviations. Mostly it's fine, you always de-abbreviated, but this VCO abbreviation, it's
a voltage controlled oscillator.
430 times in your dissertation. Never explained what it is. I think it is small thing definitely. Yeah. Okay. So and a little bit. Yes, maybe we can go to the first the main part of page 14. If you're there, okay. And it might be also a typo when you say that phase detector, the output of the phase detector is. K, la la la. It's a third
Mhm.
string
Yeah, I see.
from this. Yeah, is it a typo? Because what I read from the figure, the output
Yeah,
is
yeah.
so no
Sure,
K,
it's
no
a
K
typo.
there.
It should be varphy here. So
Okay.
it's
Good. So, and if I will try with all my effort to try to bridge what you have done to what I understand in the topic, so could we consider in this basic diagram on figure 2? So we have some generator.
yes.
Yes, it is some circuit. There is
Yes, it's
certain
a
feedback,
circuit,
yes.
yes.
And the master signal somehow tells, so I want you to run with this frequency,
Yes.
and the phase should be controlled, right?
Yes, that's
okay.
correct.
So in a way, it is at the same time as I understand what I did. It was of course lame, attempt, but I used the description in which in how to say it, in indirect forms there was frequency and there were state variables and I worked with them. So I saw the oscillations. Why you turn everything in phase. So all your equations are with phase, and that is what make my life difficult because for me it's different, a little bit different language, and it is definitely more advanced. Yeah, but for me that took some time to digest. But it is
Well, it's done because of the phase equations are better for analytics, and
Absolutely agree.
they are easier to do mathematics, and they are in some cases equivalent to the signal space. But yeah, there are some methods to get from the signal space to the phase space and to operate in a slightly easier manner.
Thank you. And for me, it was interesting. That is why I learned a lot. So while going through it, and this really, as far as I'm considered, I'm learning a lot from the dissertation. If we go to definitions, definition of lock-in, hold-in, pull-in, yes, and again, I try to read it with my eyes, obviously, yeah. In a way, could we a little bit discuss, could we treat this definition as a definition of robustness of synchronizing? Robustness of synchronizing, because you provide a range of frequencies, and you guarantee that once we started with this, with the frequency from this range, then the synchronization will happen, or
Yes.
it
yes.
is so. Is it
Yes,
like
this is about this. I wouldn't say robustness, word robustness, but I would say that while system in one of these ranges, some certain behavior of it is guaranteed.
guaranteed?
So,
yeah.
for example, for the Holden range, it's guaranteed that it will track the input frequency if it slightly changes. For the pull-in range, it's guaranteed that the synchronization will be obtained. Maybe it will take a long time,
Yeah.
but it will.
Yeah.
And as for the lock-in range that we are studying, it will not only be obtained, but also be obtained fast, and it will allow you to guarantee some behavior. So you are sure that your oscillators are no longer in desynchronization that one beat of the oscillation.
Good. So for me, it was a big relief to understand that I can see it as you have a guarantee of certain nonlinear process over the set of variables, parameters, or whatever. And this is we can possibly formulate it as, let's say, we call the system. Let me try to apply my language. They call it robust. So synchronizing is robust over the range of the input frequencies, right?
Yeah.
Thank you. Good. But who knows? We already a little bit discussed it with Mikhail. That maybe I can try to evaluate this robustness range. That I mean, in the first approximation, and we can maybe compare it. So in this
Yeah,
way,
that would be interesting
very
topic,
interesting,
and how it matches standard engineering notions, because all of these ranges didn't appear just from the air. Yeah, they appeared from the engineering applications, engineering books. For example, this I cite almost all the time the book of Roland Best, and it's quite a big monography on the phase lock loops, and all these intentions we want the system to do this, this, and this were taken mostly from this book and from others, which best cited itself. So it appears from practice, and if robustness is important for practice, well, no problem, we can consider it.
Yeah, that is definitely, this result could be interpreted, because for any frequency within this range, and you define this range. What I did, I also defined the range, but quite rough. So, and mathematicians were always a model for me, because you provided exact boundary. Let's say this was not an estimation, but was an exact boundary. While we desperately were trying to have approximate result.
My work shows that it not always work, and it's okay if the estimate is tight enough to fit into the exact, actually. But if it's wrong, it may lead to unwanted behavior of the system, and maybe fallen planes, fallen satellites, lost data on transmission, and so on, which is we want to avoid. Yeah. But if you do the estimate too tight, well, it may not be applicable at all.
Absolutely. So, yeah. But from this point of view, definitely this engineering perspective of applications results are unquestionable. Also try to maybe to ask, okay, this with the frequencies are clear, but thinking to your results, you have analytical expression. It's in a kind of ugly, but it is. I mean, it exists. That links all the parameters. That means that you can also evaluate, let's say, that for this family of filters, the process the synchronization will happen, or for this family of phase detectors, the process will stable. Is it like this? Can you think? Because again, I think there is much more in your dissertation, because you also can, again, I'm thinking aloud that let's say for this type of phase detectors, so and you can describe this set and in which the process synchronizing could happen.
Well,
is it possible to develop the work, or is it already there?
It's already there, because I'm not studying here the global stability itself. It was done before, and quite a wide range of mathematical methods on this. For example, Lyapunov stability theory that allows to prove strictly that this system is globally stable and it will synchronize. For this type of filter, for this, yes, Lyapunov function construction problem, but anyway, the answer is clear and rather simple. Mm-hmm. What I'm doing here is to investigate and to study the particular property of the transient process in the system. Mm-hmm. So I want it to be fast. And this problem is not so commonly discussed and doesn't have an adequate common logic to obtain the estimate. So what is done here in the work, a single method was applied to two different systems, two classes of filters, and it worked for them. But of course, it's quite different. The proof is of each theorem is unique. It's on the same ground, but it's still unique. If one can construct a common method for this, that would be really nice. And this is actually the goal of whole studies. But anyway, we have to start from particular cases and then make it common, and more common.
Understood. Thank you so much. Interesting. I was trying in my dissertation to build, for example, in frequency domain, an area. For example, the linear part should be long for synchronizing to take place. But it's as you said exactly. This is a global stability thing, like also, but in frequency domain. Yeah, and also for types of nonlinearities. If it is possible somehow to create a family of nonlinearities, then there was rough estimations that with this type of nonlinearity within this family, synchronizing could happen or not happen. So, but
well, it's possible to use one nonlinearity to estimate another one, maybe. So yeah, and this is a good point. So because we are discussing here linear systems and piecewise linear, it's easy to integrate, but in case of, for example, sine, you can't do this. You need to build some approximation. Maybe the piecewise linear is a linear approximation of sine, but maybe if to make it more precise, it would be better. Who knows?
Thank you. Okay, if we go to page 17, and there is a theorem, and the theorem is formulated as exact locked-in frequency. It's much respect for the exact things. What I a bit was puzzled that when you refer to publication 1, and of course I wanted to prove to go through the proof, and I tried what is happening, and by the way also repeated in your next result what you claim in your paper that is called conservative, and what you write here exact. So what is wrong?
It's actually the same. So it's done according to the definition is set in my introduction in the first section. Here we consider the lock-in range. It's on the page 16 on top. As an interval of frequency errors from the pooling range such that model being in an equilibrium, in any equilibrium, synchronizes. That's exactly what I did. The system has two series of equilibriums. One of them are stable, and one of them are saddles, unstable. So, and I considered both, and trajectories and initial data in both of them. That's why it's exact. From any synchronized state, after the abrupt change, you'll get to another synchronized state without cycle slipping. What was done before is a slightly different task. It was kind of estimate based on the notion that only stable equilibrium can be used. So, and that was done before. That is the difference. Alexandrov estimate, yeah, and that's why I call it sometimes conservative, sometimes exact. It depends on the situation.
Although it creates some, because conservative. I mean, I can do it, conservative evaluation, but exact is very exciting. So when you
that's why I put it on the dissertation. It's a marketing thing.
Also, when you just at the same thing, when you talk about estimates, and sometimes you for example, you present results in the form of these diagrams of stability range, and you call it estimates. What does it mean? Estimates? You numerically estimate, or it is still a kind of conservative estimation? Because my understanding, estimates means it's not exact. Estimates like approximately. Is it not what you mean?
Exactly. You catch the point. Okay. So the problem here is that we can put exact formulas here. But if you are going to simulate them somehow, you won't be able to solve the equations analytically, unfortunately. That's why you have to apply some numerical method which has an error. Definitely. That's
okay.
why.
This type
that's why on the diagram it's an estimate, but the formula is exact.
So that's still estimate, but in a way, in a big sense, it is exact.
Yes.
Yeah, so,
in a big sense,
estimation is with the
if you are able,
of calculations, it is okay.
If you are able to solve equations exactly, then it's exact.
Yeah, and okay, and it somehow explains another question I wanted to understand. What it mean analytical numerical? So it's analytical that numerically the equation is so long that you can solve it with numerical. Okay, that is clear. Yeah, and here in this next page you say estimates. Estimates that make me kind of worrying that if I'm buying what is what is offered. Okay. The lock-in range. Thank you. That is okay. Yeah. If the figure 5, very important. I mean, I try to make the figures like this, in which case this is my estimate. This is conservative evaluation by Bongiorno criterion, and I mean this is extremely important result. And I want to understand to make sure that I understand what is happening. So the green line is your solution. That is exact. Yeah. Then that is a dashed line, blue line. It is based on linear.
Yes.
Yes, and it is even going. It is first of all, it is too conservative, if I might say. Yes.
On the left-hand side, yes, but on the right-hand side,
it's even wrong.
Yeah, it's even wrong.
Okay, and right is simply wrong. The red line, because it promises that the phenomena will happen.
And the red line is Alexandrov's estimate that was done according to the stable equilibrium only. It allows synchronization in most cases, but it's not strict and it's not exact actually. And the linear estimate is quite conservative, but it's very simple. It's based only on filter parameters, and to do it you need no math at all. So it's easy to use, it's easy to construct, and but unfortunately, it's not always correct.
Okay. And when you call a range, so it means everything that is below of this, yeah. And it is also a little bit misleading because you give estimate and you're not telling that this range is a stability range. So it could have been more. You could have saved some time of reviewer by telling that the area below. So you pick up any parameter below the range, and stability will happen. The stability of oscillation. Okay. Okay. Here is this North American aviation thing. Yeah, and then this the next result with the lead lag filter. Yes, quite. Impressive equation, analytical, this algebraic equation that you have to solve somehow numerically, and of course it's a amount. As an engineer, when you try to read it, yeah, this is engineering valuable result, and you look at this equation and you say it's very hard to use. And one more thing that is like as an engineer, if you this is a result of this calculation. And as an engineer, I become a kind of suspicious, not a suspicious, but a kind of upset, because quite a complicated formula. But when you try to calculate it, I could not say that the behavior of this curve is very complicated. So it's monotonic and it's slightly changing with parameters. So, and I immediately think what could be possible to find the approximate estimation of such a complicated formula that in fact being numerically estimated looks a little bit simple. There are no singular points, but it is a comment. I mean, as engineer to engineer.
Yeah, this is 100% correct from your side. That's why the code is also included into this dissertation, and you can ask it in digital version if you like. And yes, it's really hard to use unless it was coded, but it was. Yeah. And you can use it as a library. Actually, so
great,
no
absolutely
problem.
Very nice. So I thought maybe if you have a kind of cheap and dirty approximation of this terrible formula with the same almost behavior, maybe it could be insightful and again easy for engineers to use. But it is my let's say.
Yes, this picture has also linear estimate, cheap and dirty, but again.
Yeah, linear cheap and dirty. That is what I mostly did because I first linearized and then estimated.
It was used for ages actually, and well. Telecommunications still work, but but anyway, if you like to be precise, you have to go into such complicated formulas. And fortunately, we have tools to make them available for public by just coding them into a library and provide as an interface. Because it's a rather elegant result that you need only filter parameters and this VCO gain to obtain the lock-in frequency. You don't need any other parameters. You don't need all this math, actually. You need an interface, and it's granted. So I have a code in the appendix that gives this interface.
Absolutely right. On the same page, again, you are referring to publication 2. When I open publication 2, the title is Conservative Evaluation. So, but now you explained what you meant. So thank you. Figure 8, but we are coming to the end gradually already. Figure 8 cannot help grilling you a little bit. And when you watch it and the axis, this x-axis, it starts from 0. Because it's kind of weird.
It's weird.
Logarithmic scale. At the same time, it's like it should be somehow. If you want to indicate that it is, it is discontinued, then you have to put dashes there. Otherwise, you cannot.
No. That's not 0 by x scale. It's just misprint. So I lost one number here. It's 10 powered by 2.
Nothing is left unnoticed. You see. So this is, but it is otherwise it is a bit annoying. Yeah. Okay, that is it. That was it. Conclusions. Everything is fine. Yeah, because you start with telling applications of in your conclusions. Again, you repeat that is applied all the time. References to applications very little bit. So that is why me kind of.
Well, they get newer and newer.
Yes, yes. Good. I think that is all what came to my mind when I was reading it. Of course, it was inspirational reading in a way because I remembered what I did and how it could be bridged with what you did. Also a quick, absolutely maybe naive question, but what do you think with this high frequency, low frequency synchronization? Could be any further develop? Is it only one-to-one synchronization? Could you consider kind of because maybe it would need new definitions, because then it is you have to define what does it mean. I think I can understand what is phase synchronization in this. For example, high frequency synchronization is like a Lissajous figure. It has to be like this 8, maybe one, maybe many, but it has to be very clear. That means phase synchronization happened. That you never thought about it. You worked in this domain. That is absolutely understandable.
Yeah, well, it's an interesting topic. Fortunately, we can do something in that area, but currently I'm not aware of the good results at the topic.
Interesting. Also, it's in your further works.
Yeah, it can be definitely added to the further works.
Mm-hmm. And also need to add here it is always, I cannot say nice, but typically a rigorous research work requires description of limitations that you are simply missing. That is nice result, but it is unapplicable for this or for that. So you describe that when your result is not inapplicable. That is, it again makes life of engineer easy because he or she can really see when it is applicable, or you need high power computer to calculate these diagrams or whatever. So it is also kind of polite, but mathematicians are known to be very ignorant. That is, that's like this is my theorems, take it and go away. But I would urge as an engineer, as a member of public, please try to.
well, I know. Because all the limitations are given actually, but they are distributed through the theorem formulation and through the text, and you need to read like 5 pages of paper to get all of them together. It's quite hard to read, but that's how mathematical text is written, unfortunately. As an engineer on the background, I had problems also with getting all the conditions combined to put them into the code, because actually this 5 pages text is an extract of what was done. It's like 50 pages text, and when you need to scroll up and down finding the parameters, the limitations and so on, that's just regarding the theorem. And if you like to understand what's in the field, what's the part of the systems under consideration, you have to read the very beginning. So yes, it's complicated, but fortunately some classification can be done on this. And this is again a topic of maybe scientific referencing, that you were forced to read my included articles to understand topic more, and actually if you try to read them, you will be forced to read others' publications and others and others and others. That's how science works, and well, it would be nice to have everything in one place, but it would be like this book.
Okay, I have to take it, because in this final conclusion of any paper, let's say in engineering, maybe not in math, you describe what was research question, you answer it with the iron in your voice that this is an answer. You describe future works that is possible also, formulated at the same time. It is a kind of, again, interface of communication when you describe what are the limitations, because then it is quite understandable now that is, and by the way, then if opponent or if a reviewer complains about some, but you say it wasn't limitation. It was a disclaimer. It saves, also lives.
Yeah, sure. You're 100% correct on this.
also need to say, but I'm coming to conclusion maybe in a way. So there's what I would love to see, this typical part that is called overview. And frankly speaking, I went through all your publications, and overview part, when you're reviewing work of others, does not leave the whole picture. I mean, when I ask, for example, how many scientists are working on this topic in the world, from which countries they are, and then you can make this landscape with a couple of clicks in Web of Science, and then you present the big picture, and then you see that, okay, this whole community of people who are working on this problem would be worth, I don't know, 200 papers per year. And then we can understand, compare to others. And it is, again, this kind of mathematical ignorance that is like for poor people. But it will make interface nicer. And it is a little bit also showing your qualification. Because you make a kind of zoom out and you present the problem in a way that is, I mean, demonstrates your ability to zoom in and zoom out too. Also, these little nice chapters when you describe, okay, what was the goal, what were the instruments, all this kind of typically met in, especially in Western dissertation parts, when you have to at philosophical level to demonstrate, to talk a little bit, because again, it is a qualification work. I think I am done with everything. Again, I have to conclude that this is excellent work. Yes. Sorry. Yes. It's a formal conclusion is that I carefully reviewed the work, and I have to conclude that it is a new word in nonlinear science, and definitely the author has demonstrated really high mathematical qualification and the qualification of researcher. All the statements are formulated very neat, and all of them are provided exact logical mathematical proof that is quite hard to meet in engineering science, I would say. Yes, that is why I believe that the author of this citation deserved, to my opinion, to be called doctor. That is, thank you.
Thank you, Leonid Sergeyevich. If anyone has any critical comments to make on my dissertation, please ask Kustas for the floor.
So as nowadays we have hybrid format, and if there is no question from the auditorium, I would suggest we will wait a couple of minutes, because we can have questions through my phone. Okay, since there are no questions through my phone and no questions here, I declare the public examination is now concluded.
Okay, we go to.
It's finally completed.
Finally complete.
Yeah.
But it was very good opponent.